Hi, so in this video we're going to talk about equations for lines or linear functions and various ways that they can be represented. So, um, the underlying thing we want to remember is that linear functions are graphically represented by lines which have constant rates of change. So, the most standard way you'll see to express a line or a linear function, the graph of a line or a linear function, is y equals mx plus b, where what we want to think about is that the m is the slope of the line, whether or not it goes up or it goes down, is it shallow, is it steep, that sort of thing, and the b is the y-intercept, or what we want to think of that as like the starting point. So the idea behind this is if you have your x and y axes, the b tells you maybe where on this on the y-axis you start out, and then what the m, the slope, tells you is what direction you're traveling in uh, from there, whether or not you're sloping downwards, sloping upwards, or constant, and if you're sloping downwards or upwards, by how much. Now, the way that slope is computed is by the change in the y values over the change in the x values. And what that means is, remember what we described in the previous video was that linear functions are characterized by having constant rates of change. So that means if I go over to the right, or if I increase x by some amount, I should increase or decrease y by some constant amount, and that constant amount is this slope. So in our scenario here, we're looking at, you know, some change in y corresponding for every change in x. Now, what makes linear functions special is that no matter where I choose to measure this delta x or change in x, and how wide or narrow of a band I choose to measure it over, the corresponding change in y values should uh, always be the same ratio to that change in x. So over here I have a example of a linear function, say minus 1x plus 4. So this minus 1 plays the role of the slope, and 4 plays the role of the intercept. So we can see when y is 0, or when x is 0, y is 4, as we expect. And what it means to have slope negative 1 is that no matter how much I change my x value, when I look at the corresponding y values, the change in y divided by the change in x is always negative 1. So if I shrink this region, that change and that change, if I take that quotient, that's still negative 1. If I pull this all the way down here, that change in y and that change in x, their quotient here is still negative 1. So we'll see this y equals mx plus b form as the most standard because it's the easiest out of which to compute the y values given some x value. So let's go ahead and clear all this. Let's say I wanted to graph something like y equals 2x plus 3. What all this information is telling me is I'm starting at 3, and then every time I increase x by 1, the y value should be going up by 2, right? So when x is 0, y should be 3. When x is 1, y should be 5. When x is 2, y should be 7. And if we graph y equals 2x plus 3, then we can see that, right? And then to verify that it corresponds to what we've been saying here, 0, 3, 1, 5, 2, 7, all these points fall straight on our line, right? All right. Okay, so the next type of form that we often see linear functions described as, or lines in general described as, is the so-called standard form. Which looks like ax plus by equals c. Now, the reason that this is called the standard form is not because this is a more convenient way of writing out linear equations or linear or the graphs of lines. Far from it. This may be the most cumbersome form, but it most resembles the form for other geometric objects like parabolas or circles or ellipses, and it also allows you to draw lines that aren't necessarily representable as functions, like vertical lines, right, by letting the b be 0. So what we want to note is that as long as b is not 0, that this is really not that different from the vertex, the points, the slope-intercept form. So what we can see is that if I go ahead and just do some algebra, what we've achieved is something that looks a lot like the slope-intercept form. Or not the slope-intercept form, the slope-intercept form, sorry. Right? Just by shifting some things over, we can go ahead and see that everything that's representable by a slope-intercept form can be representable as a standard form linear equation, and as long as b is not 0, everything that's in standard form is expressible as slope-intercept. Now we should note that these aren't the same b, right? It's a totally different thing we're describing up here than over here. So that's something you want to keep in mind. So if I wanted to say plot something like 3x plus 5y equals 2, what we note is that we can express this as 5y is equal to minus 3x plus 2, and so y is minus 3/5 x plus 2/5, and that gives us the slope-intercept form for this particular linear equation. So if I go ahead and plot y equals minus 3/5 x plus 2/5, we get the graph for our line. But the nice thing about technology is that you don't have to necessarily go through all of this trouble if all you want is a graph of the line. We may want this form for convenience sake and for other reasons, but if all we wanted was just the graph of the line, then what we could see here is we could just plot that form indirectly. And we have that these are in fact described in the same line. So those are two of our sort of regularly occurring forms for linear functions. The last one is something called the point slope form. And to get a feel for this, we want to think back on what we said earlier about graphing lines. It's true that you could start at the y-intercept and then draw upwards or downwards or horizontally based on your slope, but there's no reason you couldn't do that like with any point anywhere, right? I could pick any old random point in space, and I can draw a line through it with some slope, and that should define some sort of line or linear function. And so the point slope form has the form y equals m x minus x naught plus y naught, where x naught and y naught are some arbitrary point in the space that lies on this line. So to see why this is a sensible equation for or sensible way to express a linear function, let's work out a concrete example. 2x minus 6 maybe plus 1. And what this is telling me is that this is trying to describe a line that passes through the points 6, 1 with slope 2. Now, the reason that this is, we know that this line passes through point 6 or the point 6, 1 is if I evaluate x at 6, right? If I throw 6 in for x, as in this 6 here, this expression goes to 0, right? So this goes to 0, and so this whole thing is 0, and what I'm left with is 1. And so when x is 6, my y value is 1. So this line in fact passes through that point. Now if we wanted to see what this line looked like in slope-intercept form, we just note that I could take the point slope form and then simply distribute the 2 through the parentheses here, and that gives me my point slope form. Or sorry, my slope intercept form. So then let's take a look at what all of this would look like. Let's take a look at 2x minus 6 plus 1. And there we go. Let's go ahead and plot the point 6, 1 to see if we've hit it. And there we go. Our line passes through that point. And if we go ahead and plot our other equation, y equals 2x minus 11, we see once again we've drawn the same line. So hopefully this gives a good overview of the different types of forms a linear equation could take on, or a linear function could take on. Thank you very much. If you have any questions, please again let me know. Thank you.